Why can you not just leave your old car sitting in the backyard? Well, first of all, it is illegal, unless you live somewhere where keeping a car on bricks in your yard is completely fine. Second, old cars leak fluids, motor oil, antifreeze, transmission fluid, that can seriously damage the environment. Third, they take up space that could be used for something better, like a new car or even a barbecue grill. So, what are your options? If your car is still somewhat functional, you can sell it for parts. Even if the engine is done for, many components still have value. The battery, if it is still working, can be sold separately or taken to a recycling center. Tires, if the tread is still decent, can be resold. The catalytic converter contains precious metals like platinum, palladium, and rhodium, making it highly valuable. Headlights, mirrors, doors, there is always someone looking for replacement parts. You can sell them on Facebook Marketplace, Craigslist, or local auto shops that buy used parts. If your car is so far gone that even a tow truck refuses to take it, scrapping it for metal is the way to go. On average, scrap metal prices range from $100 to $300 per 2,000 pounds, meaning a regular sedan could get you anywhere from $200 to $600. Before dropping it off, make sure you have the proper paperwork, remove all personal belongings from the interior, and if possible, drain the fluids. Many scrapyards will pick up the car themselves, especially if it is undrivable. How about donating it to charity? In the United States, plenty of organizations accept cars as donations, even if they are not running. Some examples include Cars for Kids, Goodwill car donations, and Wheels for Wishes. You just make a call, they tow it away, and you get a tax deduction. Plus, it feels good knowing your old clunker is helping someone in need. From time to time, government programs allow you to trade in an old vehicle for compensation. In California, for instance, the Consumer Assistance Program offers up to $1,500 for cars that fail to meet environmental standards. It is worth checking if similar programs exist in your state because this might be the most profitable option. Do not leave your car abandoned on the street. That could result in fines or impoundment. Do not try to dismantle it yourself unless you know what you are doing. Some parts, like the fuel tank or battery, can be hazardous. And do not confuse proper recycling with illegal sales. Many states have strict regulations about selling non-operational vehicles without the right documentation. The key is doing it correctly to avoid trouble and protect the environment. In movies, we often see massive junkyards filled with rusting cars under the scorching sun. In reality, most vehicles do not just sit there. Modern recycling is a well-organized process where nearly 90% of materials get repurposed. If a car is beyond repair, it moves on to the dismantling stage. You already know about the initial teardown. After that, the car goes into a hydraulic press, the same machine you have probably seen in movies. It compresses the car into a compact cube, reducing its size by several times. These crushed cars are then sent to massive industrial shredders, huge machines that literally rip the car apart. After that, the shredded metal and plastic move on to sorting. Sorting is done using magnetic separators, which separate metals. Steel and iron are the easiest to extract since they are attracted to magnets. Aluminum, copper, and brass are removed using eddy currents and other techniques. Plastics, glass, and rubber are collected separately, although not everything can be recycled. Once sorted, the materials go to specialized recycling plants. Steel and aluminum are melted down and used to manufacture new cars, construction materials, household appliances, and more. Wheel rims and engine blocks are often turned into new auto parts. Components like bumpers, dashboards, and interior panels are shredded and reused for making furniture, insulation, or even new cars. Automotive glass contains a plastic layer inside, making it harder to recycle, but some companies repurpose it into construction materials. Tires do not decompose and are an environmental hazard, so they are repurposed as much as possible. They are turned into asphalt granules, rubber flooring for playgrounds, and even fuel for cement plants. 99% of car batteries are recycled. The lead is melted down, and the acid is either neutralized or reused. Despite all these processes, about 10 to 20% of car waste remains non-recyclable. This includes certain plastics, adhesive materials in upholstery, and textile or leather interior elements. Researchers are working on new disposal methods, such as pyrolysis, breaking materials down at high temperatures without oxygen, or using biodegradable materials for future vehicles. Today, around 12 million cars are recycled in the United States every year, making it one of the most advanced recycling industries. But back when cars first started taking over the roads, nobody really thought about what to do with them once they stopped working. Picture the early 20th century. Ford releases the legendary Model T. Cars become affordable to the masses, but what happens when they break down? In the early 1900s, old cars were often just left on the roadside or dumped in forests. Many were abandoned in backyards, slowly swallowed by weeds. Some cities even tossed them into rivers or burned them, simply because there was no system in place. Over time, scrapyards emerged, where enterprising individuals collected metal from wrecked cars, melted it down, and repurposed it. By the 1920s and 30s, metal was in high demand for construction, turning old cars into valuable resources. During World War II, the United States and Europe faced an enormous need for steel and other metals. Suddenly, junk cars became a gold mine. Governments even encouraged citizens to turn in their abandoned vehicles for scrap to produce tanks, weapons, and military equipment. By the end of the war, car recycling had become a structured industry, and businesses started opening specialized vehicle recycling plants. In the 1950s and 60s, cars became more affordable. People bought them in droves, and just as quickly discarded old models. Huge car graveyards emerged, where vehicles simply rusted away, taking up massive amounts of space. Soon, environmentalists raised concerns: oil leaks, gasoline spills, lead contamination. Gasoline still contained lead back then, and other toxins were polluting the land and water. This pushed governments worldwide to implement stricter recycling regulations. By the 1970s, the first serious car recycling programs were introduced. Since the 1980s, vehicle recycling has become more systematized. Companies started using automated shredders to rapidly dismantle cars. Today, modern cars are about 80% recyclable, but manufacturers are working to push that number up by another 10%. In Japan and Europe, laws require automakers to take back their old models for recycling, encouraging the production of more eco-friendly vehicles. Recycling metal from old cars saves up to 74% of the energy compared to producing new metal. Some countries have extremely strict environmental standards: Germany, Switzerland, and Japan. In these places, before cars are crushed, they are burned in specialized facilities to remove plastic residues and other combustible materials. Sounds interesting? Absolutely. This process, called pyrolysis, happens in industrial furnaces designed for thermal decomposition. Once the vehicle fluids are drained and key components are removed, the car is placed in a high-temperature chamber. The temperature inside ranges from 800 to 1,200 degrees Fahrenheit. Materials break down without oxygen, causing plastics, adhesives, textiles, and other organic materials to evaporate, leaving behind only the metal frame. The gaseous byproducts go through advanced filtration systems to capture heavy metals and toxic compounds. The result: minimal emissions and a cleaned-out metal shell, ready for crushing or smelting. Every single day, at the Lockheed Martin factory in Fort Worth, Texas, fighter jets roll off the production line, ready to dominate the skies. This is where the legendary F-16 Fighting Falcon is assembled, each one a true engineering marvel. In just 52 days, hundreds of specialists, robotic systems, and thousands of components come together to create a combat machine capable of reaching speeds of 1,500 miles per hour. How is this steel predator built? I visited the factory and saw it all with my own eyes. Ready to dive into the heart of aircraft manufacturing? Buckle up, we are taking off. At the massive Lockheed Martin factory in Fort Worth, Texas, the day begins with the roar of machinery. Gets the adrenaline pumping, right? My heart is racing. Here, In the heart of aerospace engineering, one of the most famous fighter jets in the world, the F-16 Fighting Falcon, is brought to life. But the process of building each F-16 begins long before the first part arrives at the factory. Engineers at Lockheed Martin start by working with 3D modeling systems using CATIA V5 and Siemens NX software. A digital twin of the aircraft is created to test virtual aerodynamics, simulate material strength, and optimize the placement of cables, pipelines, and electronic systems. After that, supercomputers run numerous simulations to predict how the F-16 will perform at different speeds, in combat maneuvers, or under extreme temperatures. To test the strength of the structure, prototypes of key components, such as the wings, nose section, and tail, are built and subjected to rigorous lab tests. They undergo vibration-resistant simulations to mimic turbulence, as well as extreme temperature exposure, heating up to 302 degrees and cooling down to minus 76 degrees Fahrenheit. And let's not forget impact resistance tests, like simulating a bird strike at 559 miles per hour. You love crash tests too, right? It is thrilling. Meanwhile, a separate team works on the cockpit. Test pilots evaluate the ergonomics of the instruments, the positioning of the HUD display, and the ease of control. As for the materials, supply issues are never a concern. Lockheed Martin signs contracts 2 to 3 years in advance. The standard material set includes aluminum and titanium alloys from Alcoa and Timet, which form the fuselage structure, composite materials from Toray and Hexil, used for wings, fairings, and radar-absorbing elements. Aerospace electronic systems, including radars, avionics, and targeting systems, are provided by Northrop Grumman and Raytheon. In the morning, the factory floor at Lockheed Martin has a quiet but focused atmosphere. This is not just manufacturing. This is where fighter jets that will rule the skies are born. Workers are at their stations. Some are prepping riveting guns. Others are reviewing blueprints, while some are operating laser measuring systems. Today, another F-16 Fighting Falcon is being assembled, and everything must be flawless. As you might have guessed, the factory follows a modular approach. Instead of building an entire jet in one place, it is assembled in sections before being joined together. In one of the workshops, the aluminum cockpit frame is already complete. Nearby tables hold avionics instruments, HUD displays, and computer system modules. Workers in white gloves carefully install them into compartments. The ejection seat mount is fitted, and a 12mm thick bulletproof canopy glass is installed, capable of withstanding a 13mm bullet impact. 12.5 miles of wiring are laid out, connecting sensors, displays, and control systems. Meanwhile, the central fuselage section is being assembled, the area that houses the fuel tanks, landing gear, and wing mounting points. A large aluminum frame is secured with 40,000 rivets installed by automated riveting robots. Fuel tanks with a total capacity of 845 gallons are integrated into the structure. The landing gear, capable of handling loads up to 44,000 pounds, is installed and tested. Workers meticulously check the tanks for leaks by filling them with a special gas and inspecting for any seepage. In the adjacent workshop, the tail section takes shape. It is welded together using titanium and composite panels, with an engine mount already in place, designed to withstand temperatures exceeding 2,192 degrees Fahrenheit. The elevator and rudder are then installed, followed by a check on the emergency braking mechanism. A specialized team handles this section since the tail not only controls flight, but also maintains the jet's overall balance. The wings are assembled in a dedicated section. Hydraulic mechanisms for controlling flaps and ailerons are installed, along with hardpoints for weapons. The composite wing surfaces undergo ultrasonic testing for defects. If even one layer of carbon fiber is improperly placed, the wing could deform under combat stress. So there is zero tolerance for errors. Once all modules pass rigorous inspections, they are transported to the final assembly line. The final assembly line is a massive hangar stretching 437 yards long, where hundreds of specialists work in precise coordination. Everything follows a strict schedule. Any delay in one step can impact the entire process. The central fuselage is lifted by a specialized crane and aligned using lasers. First, the cockpit is attached, followed by the tail section. Engineers use high-strength titanium bolts capable of withstanding loads of approximately 88,180 pounds. Once the primary structure is complete, it is time to attach the wings, which are secured with reinforced titanium joints to ensure structural rigidity. Engineers meticulously check the alignment angles to ensure the error margin does not exceed allowable limits. After assembling the airframe, one of the most critical moments arrives: the installation of the jet engine. It is transported in a specialized container and lifted into the tail section using a hydraulic hoist. Technicians carefully connect all systems: fuel lines, hydraulic and electrical cables, and the afterburner system that enables supersonic flight. Once installed, a dry test run is conducted to verify its operation without fuel ignition. The onboard computer, pilot displays, weapons control systems, and the ANAPG-83 radar, capable of detecting targets at a range of 100 miles, are then integrated. Before the first flight, the F-16 receives anti-corrosion treatment, paint, and stealth coating. As a kid, my best friend was obsessed with origami. She was into everything from Eastern culture, so origami never stood a chance of being ignored. Me? I was terrible at it. My fine motor skills were not exactly top-notch, so while she was crafting intricate dragons and delicate flowers, I was busy making paper planes of all sizes and launching them from my window into the backyard. Could I have imagined back then that I would one day step into the legendary Lockheed Martin factory and witness the birth of an F-16 with my own eyes? Absolutely not. Before an F-16 takes to the skies, it must undergo a series of ground tests. Every flight system, electronics, fuel supply, and hydraulics is tested on the ground first. The engine is warmed up to operational temperature, and the exhaust system and airflow temperature in the ducts are inspected. Special attention is given to the ACES-2 ejection seat and emergency systems that might be needed in a crisis. Once all ground systems pass, the pilot receives clearance for the first flight. Communication with ground controllers and engineers is checked in real time. The jet slowly rolls toward the runway, then accelerates to around 3,000 yards per hour for an optimal takeoff. After liftoff, the landing gear retracts smoothly. Everything is functioning perfectly. At an altitude of around 3,300 yards, the pilot executes the first maneuvers, testing aerodynamics, elevator, aileron, and flap responses at different speeds. The F-16 is then pushed past Mach 1 to test the afterburner system. This phase measures aerodynamic stress, identifying any defects at high speeds. G-force tests follow, as the pilot executes precise maneuvers to ensure stability under varying attack angles and velocities. After completing initial flight tests, the pilot begins the descent. At 3,000 yards, the landing gear deploys, and the pilot prepares for touchdown. The effectiveness of brakes and the auto-stabilization system is evaluated. The moment the F-16 touches the ground, it decelerates quickly. Engineers conduct final inspections of electronics, fuel systems, and structural integrity. Data is then analyzed, and if everything checks out, the F-16 is officially cleared for duty. Every single day, airplanes across the world consume more than 5 million barrels of aviation fuel. This fuel is the lifeblood of aviation. Without it, not a single jetliner would take off. But have you ever wondered how it is made? From oil refineries to the ultra-pure tanks inside aircraft, the journey of jet fuel is packed with chemical secrets, strict regulations, and even technologies originally developed for military fighter jets. Today, we are pulling back the curtain on this fascinating process and uncovering all its secrets. Jet fuel is a crucial component of the aviation industry. It must meet stringent quality standards to ensure the stable operation of both turbojet and turboprop engines. The primary source for jet fuel production is crude oil, which undergoes a complex technological journey from extraction to the final product. It was obtained through the distillation of crude oil. In the year 1903, the Wright brothers made the first controlled flight with the Wright Flyer, powered by a gasoline engine. In the early days of aviation, gasoline remained the primary fuel, as piston aircraft engines required a high degree of fuel volatility. However, during the 1920s and 1930s, engineers began considering kerosene as an alternative to gasoline due to its higher energy density, making it more suitable for high-altitude flights. German engineer Hans von Ohain and British designer Frank Whittle independently developed the first operational jet engines. Can you believe it? It is true what they say. Ideas are in the air. So, in the year 1939, Germany tested the first jet aircraft, the Heinkel He 178, which ran on specially refined kerosene. In the year 1941, Britain responded to the Nazis by launching the Gloucester E into production, the first British jet aircraft. Around the same time, engineers began developing special types of kerosene that met the demands of jet engines. Military nations involved in the war experimented with various fuel formulations to ensure high energy density, resistance to low temperatures, and low corrosiveness for fuel systems. During the war, jet fuel had a primitive composition, but over time, its standards improved significantly. After the devastating Second World War, jet aviation began rapidly advancing. This created a demand for improved fuel that could provide reliability at high altitudes, better thermal stability, and the absence of harmful impurities. In the 1950s, the first standardized types of jet fuel emerged. Let's take a look at them. JP-1, developed in the year 1944, was an early standard for military aviation. JP-4, introduced in the year 1950, was a blend of kerosene and gasoline that improved performance in cold temperatures. JP-5, introduced in the year 1952, had a higher flash point and was used on US aircraft carriers. Commercial aviation also introduced its own standards, and in the 1950s, Jet A and Jet A1 were introduced as the primary fuels for commercial aircraft. With the development of supersonic aviation, such as the Concorde, and new generation military aircraft, the demand for higher quality fuel increased. Fuel now needed a lower freezing point, as flights took place at extremely high altitudes. This led to the introduction of anti-static and anti-corrosion additives, improving safety. Fuel systems were also designed to prevent icing, as jet fuel could cool down to -40 degrees Fahrenheit or lower. In the 1980s, the military adopted JP-8, replacing JP-4. This new standard contained fewer volatile components, making it safer to store and transport. The 1990s marked the beginning of the modern era of jet fuel production. So, let's move on to the steps involved in making jet fuel today, starting with crude oil extraction. Jet fuel is derived from hydrocarbons found in crude oil or natural gas. There are several methods for extracting crude oil. The first method is natural pressure extraction, where oil flows to the surface due to its own pressure. This is common in young oil fields. The second method is mechanical pumping, where pumps are used to lift the liquid to the surface. The third method is secondary recovery, where water or gas is injected into the reservoir to increase pressure and stimulate oil flow. Once extracted, crude oil contains impurities such as water, gases, and solid particles that must be removed before refining. Before transportation to the refinery, crude oil undergoes purification. First, water is separated using separators and chemical agents to remove emulsions. Next, degassing removes light gaseous hydrocarbons. Finally, filtration removes solid particles. In storage tanks, the flow slows down, allowing heavier particles to settle, while lighter fractions rise to the top. After this preparation, crude oil is transported to refineries through pipelines or by tanker ships. The next step is the separation of crude oil into different fractions. Let me explain how this process works. The process begins by heating crude oil to temperatures between 662 and 752 degrees Fahrenheit inside a massive distillation column. Through evaporation and condensation, we obtain different fractions: gaseous hydrocarbons, gasoline, kerosene, diesel fuel, and residual fuel oil. The gaseous hydrocarbons include methane, ethane, propane, and butane. The kerosene fraction serves as the primary raw material for jet fuel and undergoes further purification. To improve the quality of the kerosene fraction, it is treated to remove sulfur, nitrogen, and oxygen-containing compounds through hydroprocessing. This process occurs under pressures ranging from 30 to 80 atmospheres and at temperatures between 572 and 752 degrees Fahrenheit, using catalysts such as nickel molybdenum or cobalt molybdenum compounds. As a result, sulfur content is reduced, minimizing corrosion and harmful emissions. Additionally, fuel stability improves, allowing for longer storage without sediment formation. If crude oil does not contain enough kerosene fraction, catalytic cracking or hydrocracking is used to break heavier fractions into lighter ones. Catalytic cracking employs catalysts to break large molecules into smaller ones, while hydrocracking uses hydrogen to produce stable hydrocarbons. These processes help increase the yield of kerosene for jet fuel. After purification and modification, special additives are added to the kerosene fraction to enhance its properties. Antioxidants prevent sediment formation and maintain fuel system cleanliness. Anti-static additives reduce the risk of electrostatic charge buildup during refueling. Anti-corrosion agents protect fuel tanks from corrosion. Anti-freezing additives ensure stability at low temperatures. After additives are introduced, the fuel undergoes final filtration and preparation for distribution. To meet international standards, jet fuel undergoes strict quality testing. Viscosity determines fluidity at low temperatures. The freezing point for Jet A1 must not exceed -52.6 degrees Fahrenheit. The heat of combustion must be at least 18,400 British thermal units per pound. Water content must not exceed 0.46 two-thousandths of a grain. Electrical conductivity ensures safe refueling without sparks. If the fuel fails to meet standards, it is sent for reprocessing. And now, we reach the final stage of our journey. The finished jet fuel is stored in tanks with moisture and temperature protection. It is transported primarily through pipelines to airports. Large volumes are shipped by rail tankers. Tanker ships handle international deliveries. Trucks deliver fuel to remote airports. During transportation, it is crucial to prevent contamination with water or foreign substances that could compromise fuel quality. By the year 2025, the United States is projected to consume nearly 2 million barrels of aviation fuel per day, totaling approximately 86 million tons per year. As one of the world's largest consumers of jet fuel, the global demand is expected to be significantly higher. The aviation industry is actively working on developing renewable jet fuels to reduce greenhouse gas emissions and improve sustainability. With advancements in technology and environmental regulations, the future will see wider use of biofuels and synthetic alternatives, making aviation more eco-friendly. And most importantly, jet fuel keeps airplanes flying. The next time you board a plane for a vacation or business trip, remember the complex production process that brought that fuel to the aircraft. I think it is worth it. What do you think? Imagine this, a house printed in just 24 hours. Sounds like science fiction, right? But it's real. Back in 2018, the United States saw its very first 3D printed house. Today, there are hundreds of these homes, and the numbers keep growing. This technology doesn't just build houses. It's redefining architecture with designs that are both stunning and efficient. And the best part? A home like this could cost as little as $10,000. Ready to see how a giant printer turns concrete into cozy living spaces? Let's dive in. The first 3D printed house in the US appeared in 2018. Now, there are hundreds of these homes, and the count is steadily climbing. Let's start with the basics. 3D printing is a technology that creates objects layer by layer using specific materials. When it comes to houses, this means a massive 3D printer extrudes concrete or other construction materials based on a pre-designed blueprint. Think of squeezing frosting from a piping bag, except instead of frosting, it's concrete, and instead of a cake, it's a fully functional house. These 3D printers are no small feat. They're massive. Imagine a structure the size of a small crane or a garage hangar. For example, Icon, a Texas-based company, uses a system called Vulcan. This printer stands about 11 feet tall and spans over 32 feet in width. Its modular design allows it to expand and adapt to the size of the house being built. The printer operates on rails or special platforms, moving around the construction site. That's why it can print anything from a tiny cottage to a spacious home. Essentially, it's like a large truck, a smart, precise machine that gets the job done with remarkable accuracy. Let me tell you about my visit to one of these construction sites. Icon, based in Texas, invited me to see their house printing process up close. And let me tell you, watching this gigantic printer in action makes you feel like the future is already here. It all begins with architects designing the house on a computer. It's like those 3D renderings you've seen in movies or on designer websites. Depending on the complexity of the design, creating a 3D model can take anywhere from a few hours to several weeks. A simple, single-story house without elaborate details might only take a day or two. But a complex project with unique shapes, energy-efficient features, or intricate interiors? That's a whole different ballgame. Here, architects work closely with engineers to ensure everything checks out. Will the walls hold up under pressure? Are the windows and doors positioned correctly? Are the local climate conditions accounted for? The coolest part? Modern software like AutoCAD, Revit, or SketchUp makes this process faster and allows for detailed visualization of every inch of the house. At the construction site, a massive 3D printer is set up. This printer, essentially a giant robot, moves on rails or with manipulators. It starts printing the house layer by layer. The main material? A special quick-drying concrete that becomes incredibly strong. Once the walls are done, the roof, windows, doors, and other elements are added. At this stage, traditional construction methods are used to finish the house. While the printer can handle the main structure, components like the roof, windows, and doors are typically crafted from traditional materials like wood or metal. For example, the roof might be made of metal or wood, depending on the project. Windows and doors are also custom-ordered and installed, using conventional construction techniques. This blend of innovative technology and proven materials ensures homes that are not only efficient, but also comfortable to live in. The entire process takes anywhere from a few days to a few weeks, a stark contrast to traditional construction, which can drag on for months. 3D printed homes have a ton of advantages, making them an increasingly popular choice. For starters, they can be built in just a matter of days. These houses are also significantly cheaper than traditional ones. According to Icon, a small home can cost as little as $10,000. And the designs? They're nothing short of art. This technology also minimizes waste and uses eco-friendly materials. Traditional construction often leads to a lot of leftover materials like concrete, wood, and metal, especially when cutting pieces for doors, windows, or walls. But with a 3D printer, materials are used only where needed. The printer lays down each layer precisely according to the design, leaving no excess material behind. It's not just about efficiency, it's about sustainability too. Many companies involved in 3D construction use materials that have a lower environmental impact. For instance, the concrete might include recycled components or be made with eco-friendlier ingredients, reducing pollution during production. Moreover, precise material calculations mean fewer resources are consumed, eliminating the need for extra stock or creating waste that ends up in landfills. This approach not only saves money, but also significantly reduces the environmental footprint of construction. The technology also opens doors to new types of eco-friendly materials, such as biodegradable concrete that incorporates recycled waste or organic substances. These materials reduce CO2 emissions and the need for extracting new resources. So, 3D printing isn't just speeding up construction, it's making it more sustainable and environmentally friendly. It's not just a trend, it's a real shift in the construction industry, one that could greatly improve our ecological outlook for years to come. Of course, it's not all perfect. The technology is still new and comes with its challenges. Currently, most 3D printed homes are made of concrete. But for more complex designs, new materials will need to be developed. These massive printers are also hard to transport and require specific conditions to operate. Plus, many countries don't yet have clear regulations for constructing such homes. Icon can print a house in just 24 hours. One driving factor behind this technology is its potential to address affordable housing shortages. 3D printing dramatically cuts costs on materials and labor. For example, Icon is working on a project to build homes for low-income families at just $4,000 each. The technology also unlocks incredible possibilities for architects. A 3D printer can create intricate, unconventional shapes that are almost impossible with traditional methods. Architects now have the freedom to design without limits, knowing the printer can handle any form or detail. The future of 3D printed homes looks incredibly bright. These technologies are already being used not just for housing, but also for offices, schools, and even hospitals. Icon is building the first fully 3D printed neighborhoods, including a project in the US in 2021 that delivered 5 homes to financially struggling families. And here's what blew my mind. Icon is working with NASA to print homes on Mars. Imagine that. One day, people might live in 3D printed houses not just on Earth, but on other planets too. Icon was founded in 2017 in Austin, Texas, by a group of engineers and entrepreneurs. Their goal was ambitious, yet simple: to create technology that makes housing fast, affordable, and sustainable, especially for those with limited access to traditional homes. The idea came when the founders realized the construction industry was bogged down by outdated methods and high costs for materials and labor. They envisioned 3D printing as a way to simplify the process, lower costs, and provide homes for those in need. Initially, Icon started as a small startup in the construction sector. It quickly gained traction and attracted major investments. Soon, Icon partnered with the Bjarke Ingels Group to create a groundbreaking 3D printed house, marking a significant milestone in the industry. This was the first house printed using technology that reduced material and labor costs. From there, they scaled up to build larger homes for various social programs. In the following years, Icon secured significant funding from venture capital firms, allowing them to improve their technology and expand production. For instance, in 2020, the company raised $35 million, enabling them to grow their operations and launch new projects. Imagine this: one ship contains up to 20,000 tons of steel. That's the weight of 3 Eiffel Towers. But what happens when these ocean giants retire? Every year, more than 1,000 vessels are sent for recycling, and their materials find new life in bridges, cars, and even other ships. This isn't just dismantling, it's giving metal a second life. Stick around to see how this global process is changing the world. The beginning of the end, or why are ships dismantled? Ocean vessels have an expiration date. On average, that's about 25 to 30 years. After this, maintaining them becomes uneconomical and their structures unsafe. This is where a process, often called shipbreaking, begins. Remember those movie scenes where ships are shattered by waves? Well, no waves are needed here. Just welding tools, massive cranes, and teams of workers who know how to handle these metal giants. First, everything is stripped from the ship: furniture, electronics, pipes, and cables. Even doors and windows. All of this can be recycled or reused. This process is usually carried out by hand, though sometimes specialized equipment is used. Workers physically dismantle the interior of the ship, unscrewing bolts, cutting metal pipes, removing doors, windows, and panels. It's meticulous, labor-intensive work, requiring attention to detail and strict safety protocols. Imagine this: cables need to be carefully extracted so they can be sold as copper scrap, and chemicals, such as leftover paint or lubricants, must be safely removed. Even furniture is taken apart to salvage wood or metal components. Of course, on large shipyards, workers are aided by mechanical tools, cranes, gas cutters, and sometimes robots to handle hazardous materials. But the bulk of the work is manual labor. That's why, in countries like Bangladesh or India, where labor is cheaper, shipbreaking is so popular. This stage is crucial because properly preparing a ship for dismantling prevents leaks of chemicals and toxic materials that could harm the ecosystem. Oil, fuel, and chemicals all are drained from the ship to avoid environmental contamination. Once the ship's hull is stripped of everything unnecessary, the gas cutters take center stage. Massive, rusty steel walls, the very structures that once kept the ship afloat, are gradually turned into individual pieces of metal. Workers, dressed in protective suits, stand directly on the hull. Their cutters create bright orange sparks, flying in all directions, producing a kind of steel fireworks. It's both mesmerizing and slightly intimidating. The cutter heats the metal to such a high temperature that it literally melts. But it only looks easy. Ships aren't just piles of steel. They're labyrinths of multiple layers of metal. Sometimes workers have to cut through several layers to reach the right spot. Cutting begins with the upper decks. Large sections are first carved out, like chunks of sidewalls, decks, or even parts of the hull, which are then lifted by cranes and loaded onto platforms. From there, they're sent to factories, where the pieces are recycled into new steel or aluminum. But it's not just about cutting, it's about doing it safely. That's why the hull was cleared earlier of any leftover fuel, lubricants, or other hazardous materials. Without this step, gas cutters could trigger explosions. So, this process is not just labor, it's an art that requires strict adherence to safety rules. And of course, all this happens under the blazing sun or in humid coastal climates. Workers quickly adapt to the heat, and even sparks flying at their feet become a routine sight. In the end, they witness the transformation of a massive, once indomitable ship into mere pieces of metal. It's almost like watching a rebirth. Imagine this. Those massive steel blocks that once kept a ship afloat become the foundation for new bridges, buildings, or even other ships. About 90% of a ship's materials can be recycled, and the largest share is steel. A single large ship can yield up to 20,000 tons of this metal. That's the equivalent of 3 Eiffel Towers in weight. Once the ship's hull is cut into pieces, the next thrilling phase begins, transporting the steel to factories. And trust me, it's not as simple as throwing it on a truck and driving off. These metal pieces are usually so large and heavy that they can't be moved by conventional means. Massive cranes, the kind that look like they could lift a ship themselves, dominate the scene. Their long metal arms with hooks or magnetic platforms carefully grab steel sections and lift them off the ground. It's almost like watching giant toys in action, but everything is done with surgical precision, because one mistake could be costly. After that, the steel is loaded onto huge platforms or special trucks. Regular trailers won't cut it here. You need vehicles with reinforced frames capable of bearing tons of weight. Imagine this. One section can weigh several dozen tons. Sometimes, rail cars or barges are used for transport if the factory is near a port or river. This helps cut down on delivery costs because moving steel is no cheap task. The journey to the factory can be long. For example, if a ship is dismantled somewhere in South Asia, its materials might be sent as far as Europe or America. In such cases, the metal is loaded onto ships again, but this time on cargo vessels. Full circle, right? A ship becomes raw material transported by another ship. Once at the factory, the metal is carefully weighed. Every detail matters, from the total weight to the precise composition of the metal, as different alloys require different processing. Only then does the steel head to the melting stage, where its new life begins. This steel will become new construction materials. Ships continue their legacy, not in the ocean, but as skyscrapers or train tracks. But it's not just steel that's valuable. Ship components also contain aluminum, used in car and airplane manufacturing. Wooden elements, rare in modern ships but present in older ones, are restored and sold for decor. Fabric from old seats is sometimes repurposed into bags or even rugs. Isn't that cool? You buy something stylish and later find out, oh, this was on a liner that sailed the Caribbean. But it's not all smooth sailing. Ship recycling can pose environmental risks if done irresponsibly. Ever heard of Alang? It's the world's largest ship recycling yard, located in India. There, ships are literally beached and dismantled by hand. This method is cheap, but dangerous. Oil and chemicals can leak into the water, and workers often lack proper protective gear. Recently, however, the world has started paying attention to this issue. More and more ships are being recycled at specialized yards that follow strict environmental standards. For instance, In Europe, regulations require the safe storage and disposal of hazardous materials. The largest ship ever dismantled was a container vessel measuring 1,312 feet in length. Imagine taking apart such a giant. This container ship, Ever Given, became famous in 2021 after blocking the Suez Canal, though its end wasn't due to that incident. When ships of this scale are retired, they're usually sent to one of the world's biggest shipbreaking capitals. Dismantling such a vessel likely took no less than a year, because a mountain of steel, cables, equipment, and other materials is a serious challenge, even for experienced teams. Every piece must not only be cut, but also carefully moved, sorted, and shipped for recycling. At the steel plant I visited, everything starts with thoroughly inspecting the metal pieces. They're cleaned of any paint, rust, lubricants, or other impurities that could affect the quality of the steel. Watch as dozens of hands and machines work to prepare this metal for its next journey. Next, the pieces are shredded, cut into smaller parts that are easier to load into the smelting furnace. The process of cutting metal at steel plants is a spectacle in itself, like something out of a sci-fi movie. Huge workshops filled with sparks, heat, and the hum of machinery. These aren't ordinary scissors. They're powerful hydraulic presses, cutting machines, and even lasers. Each tool plays its part depending on the size and type of metal. First up are hydraulic shears. These massive machines can slice through thick steel like paper. They operate under immense pressure, thousands of tons of force that literally crush and cut the metal. Their crunch echoes throughout the workshop. For finer work, gas or plasma cutters are used. A gas cutter operates by burning fuel. Oxygen and acetylene heat the metal until it melts, and then a stream of gas cuts through it. Plasma cutters are even cooler. They create an electric arc that melts the metal, leaving a clean, precise edge. Then there are laser machines. They work with incredible precision, carving out the tiniest details. The laser beam seems to dance across the metal's surface, leaving behind a smooth, polished cut. This is the technology of the future, already in action at many factories. But this isn't just random cutting. Every step is carefully planned. Metal is sorted by thickness and type to avoid damaging equipment. Larger pieces go through specialized conveyors to the next stage, while smaller ones are sent straight to melting. For melting steel, arc furnaces are used. These massive monsters run on electricity, generating temperatures close to 3,000 degrees Fahrenheit. The metal simply melts, transforming into liquid steel. But that's not all. Special substances, known as ferroalloys, are added to the molten mass to enhance the steel's properties. Need strength? Add vanadium or chromium. Want it lightweight? Add aluminum. It's like cooking, but for engineers. Next, the steel is poured into molds, depending on what it's destined to become. These could be sheets, beams, rebar, or even wire. The castings are cooled, cut, polished, and then shipped off for new projects. Building skyscrapers, bridges, or even new ships, all of this can start with the recycled hull of an old vessel. And isn't it amazing? A ship that once carried thousands of tons of cargo across oceans can become part of a car or the frame for a modern stadium. This second life of steel feels almost magical, doesn't it? Imagine every tire on your car as the result of decades of innovation, research, and fine-tuned manufacturing. Goodyear, one of the giants in this industry, produces tires that are engineering marvels. But how exactly are these technological masterpieces made? Let's break it down, step by step, and get a sense of the scale of this incredible work. Goodyear was founded back in 1898 and named after Charles Goodyear, the inventor of vulcanized rubber. The production of Goodyear tires begins with carefully selected raw materials. The key ingredient, of course, is rubber. But not just any rubber you'd find in a forest. This is a complex material made from natural rubber and synthetic substitutes. Natural rubber is harvested from the sap of hevea trees grown in tropical regions. This sap is called latex, a familiar term, right? The main suppliers of natural rubber are countries in Southeast Asia, like Thailand, Indonesia, Vietnam, and Malaysia. To collect the sap, neat cuts are made on the bark of hevea trees, similar to how maple syrup is gathered. Latex slowly oozes out and is collected in small containers attached to the tree trunk. A single tree produces only a small amount of latex daily, so plantations are packed with thousands of trees. Initially, latex has a liquid consistency and needs processing. Acids are added to it, causing the latex to coagulate into an elastic mass. Typically, formic acid is used. Yes, formic acid. Sounds surprising, doesn't it? The name dates back to the 1700s, when scientists first extracted this acid from ants. Back then, chemists boiled ants and discovered a liquid with peculiar properties. It turned out to be an acid that many insects, including ants and bees, use as a natural defense mechanism. Today, no one harvests formic acid from ants anymore. Instead, it's synthesized on an industrial scale from chemicals like methanol or carbon monoxide using modern technology. This method is way more efficient than collecting it from insects. Formic acid works perfectly for latex processing because it's non-toxic in small amounts. It easily coagulates the protein molecules in latex, turning the liquid into a solid elastic mass. Plus, it dissolves in water, making it easy to wash away any residue after treatment. After adding the acid, the resulting material is pressed into blocks or rolls and dried. This process significantly reduces its volume for easier transportation. The dried rubber is shipped to factories worldwide. For Goodyear, this includes plants in the United States, Germany, China, and other countries. The rubber is transported by sea in large bales that are easy to store and use in tire production. This covers natural rubber, but how do they make the synthetic kind for tires? Synthetic rubber is an artificially created material made from petroleum products. Its main component is butadiene, a chemical derived from gases left over after refining oil or natural gas. Butadiene, along with other chemicals like styrene, undergoes a process called polymerization. This chemical reaction links molecules into long chains, creating a material with high elasticity. The most common types of synthetic rubber are styrene butadiene rubber and polybutadiene rubber. To give synthetic rubber the properties needed for tires, such as strength, wear resistance, and temperature resilience, special additives are mixed in, like carbon black or silica, and plasticizers. Synthetic rubber is produced on a large industrial scale and shipped to factories in the form of granules, rolls, or preformed blocks. At Goodyear's factories, a rubber compound is created by combining the best qualities of both natural and synthetic rubbers. The rubbers are weighed precisely according to formulas tailored to specific tire models. In massive industrial mixers, the rubbers are blended with other ingredients: carbon black, silica, sulfur, oils, and chemical additives. Think of it like making dough, but under high pressure and heat. During mixing, the rubber turns into a thick black paste. This stage is crucial because it defines the tire's future characteristics: grip, durability, and temperature resistance. The mixture is repeatedly needed to ensure all components are evenly distributed. This guarantees uniformity in the final rubber. After mixing, the material is cooled and formed into large sheets, which are then cut into pieces for further tire production. The process of cutting rubber sheets at the factory is truly impressive in scale. This isn't done with kitchen knives, but with massive industrial machines that work with the precision of jewelers, but on a factory-wide scale. The thickness of the rubber sheets varies depending on the part of the tire they're meant for. For example, the layers for the tread are thicker than those for the sidewalls. Before cutting, each roll or sheet passes through an automated inspection system. Machines check for defects like air bubbles, tears, or uneven thickness. Anything that doesn't meet standards is immediately discarded. Cutting is done using specialized high-tech machines. Rotary knives, resembling spinning discs, effortlessly slice through the rubber, creating perfectly straight strips. Lasers, the most advanced technology, can cut rubber without physical contact, ensuring extraordinary precision. The laser beam literally melts the material at the desired spot, leaving a flawlessly smooth edge. Depending on the production stage, Sheets may be cut into long, narrow strips for tire reinforcement or left in large pieces for the tread. Everything is programmed, and parameters are automatically adjusted based on the type of tire being made. After cutting, materials are sorted by type and size. Strips are rolled up, and sheets are stacked. All of this is transported to the next department for tire assembly. Each machine processes thousands of feet of rubber daily. Powerful engines roar, knives spin at incredible speeds, and workers monitor everything through computers. This conveyor never stops, producing hundreds of tires every hour. It's like surgery on an industrial scale. Everything must be flawlessly precise to ensure the finished tire is safe and high quality. Goodyear is one of the world's leading tire manufacturers, with production facilities in 22 countries and 52 factories. Let's circle back to another fascinating aspect of this story: the ingredients beyond rubber. Why are they added? Carbon black gives the tire strength and protection against UV rays. Silica improves road grip, especially in wet conditions. Sulfur and other chemicals help rubber retain its shape and elasticity under different conditions. As you can see, every detail matters. But that's not all. Let me tell you about the skeleton of the tire. You know it's not just rubber, right? The core consists of a multi-layered structure. The quality of this framework determines the tire's strength, durability, and ability to support the weight of the vehicle. This process involves several sequential and high-tech operations. But first, let's look at the materials. Textile cords are a must in the tire's construction. These are threads made of polyester, nylon, or even aramid, a highly durable synthetic fiber. They provide flexibility and lightness. Steel cords are also added. These are thin yet incredibly strong metal wires that give the framework rigidity and the ability to withstand heavy loads. Rubber acts as the bonding material between the layers of cord, creating a strong yet elastic structure. Cords pass through specialized machines that evenly coat them with rubber. This binds the fibers together, protects the textile or metal from moisture and corrosion, and ensures a strong bond with other rubber layers during vulcanization. This process is incredibly precise. If the rubber layer is too thick or too thin, it could compromise the tire's safety. Next comes the breaker. This part of the framework lies between the tread and the tire's core. Its job is to distribute the load across the tire and protect it from punctures. The breaker is made of multiple layers of steel cord laid at specific angles. Each layer is cut to a template and laid out in a precise sequence on specialized drums. The angles are computer-controlled to achieve the desired characteristics. The main framework is assembled on a special building drum that rotates, allowing all layers to be evenly laid out. First, textile layers are added for flexibility. Then, metal wire rings are added to form rigid sidewalls. These rings help the tire stay firmly on the rim. The tire bead, its inner edge that contacts the wheel, must be extremely strong. The bead ring is made from multi-layered steel strips coated in rubber. Side layers of rubber are added to the main framework to protect the tire from damage. This entire sandwich is secured on the drum using pressure and heat. Every single day, millions of batteries end up in landfills, posing a serious threat to the environment. But what if I told you those old batteries hold rare metals that can power the technologies of tomorrow? Lithium for electric vehicles, nickel for wind turbines, cobalt for medical devices, all hidden within the process of recycling. Want to know how toxic waste transforms into resources for the future? Stick around. An incredible process awaits. Battery collection starts with people. Individuals drop off batteries from phones and laptops. Auto repair shops contribute electric vehicle batteries, and businesses with lots of equipment also pitch in. Collection points can be found in electronics stores, supermarkets, or specialized recycling centers. This process is mostly hands-on. People bring in batteries, and staff or volunteers accept and log them. Large volumes of batteries from factories or auto repair shops are delivered by trucks to major collection centers. Specialized battery containers come equipped with sensors to detect their fill level. When a container is nearly full, it sends a signal to the recycling company. Some companies even use drones to check the status of large containers in remote locations. Batteries are sorted by type using both people and machines, as different batteries, like lithium-ion, nickel metal hydride, or lead-acid, can't be recycled together. At smaller collection points, like those in cities, workers manually sort batteries by examining labels, markings, and physical characteristics such as shape or color. Small batteries from smartphones or laptops are sorted one way, while larger electric vehicle batteries take a different path. At larger facilities, automated sorting lines take over. Machines scan batteries based on their size, weight, and the metals they contain. Advanced tools like X-ray analysis or spectroscopy determine the type of battery in front of them. Once scanned, batteries move along conveyors into designated bins, where they wait for the next stage. Even at automated factories, people are still part of the process. Operators ensure machines are sorting batteries correctly. If a problem arises, like a damaged battery case or missing label, workers step in to sort them manually. Batteries from electric vehicles or solar power systems are often too large for automated lines. This is where robots come in, helping dismantle these massive units into smaller sections, which are then sorted by material. No matter how much machines can do, people are still the heart of the sorting process. Most of the work is handled by employees at collection points and operators of sorting lines. Experts manually inspect damaged batteries, because machines haven't yet mastered the ability to detect every defect. Sure, machines are faster, but we can't do without human oversight just yet. In the end, every properly sorted battery is another chance to recover rare earth metals and reduce environmental harm. Next up, the batteries get shredded, like entering a pair of massive steel jaws. They're loaded into a machine that looks like a giant shredder, armed with industrial-grade steel blades. These blades are so powerful they can tear apart an electric vehicle's battery casing. The scene is pure metallic chaos. The sound of ripping, grinding, and snapping as the batteries are literally torn to pieces. Since batteries may still hold a charge, they're first frozen in liquid nitrogen. This cools the metals and minimizes the risk of fire. Some shredders operate in sealed chambers filled with inert gases to prevent contact with oxygen. There's even a more dramatic approach. In some facilities, batteries are burned with controlled electrical currents, leaving only the metals behind. The batteries are shredded into pieces ranging from several inches to fine powder, depending on the type of shredder. The blades spin at over 2,000 revolutions per minute, sending metal fragments clanging and crashing inside a protective chamber. The shredded material then moves through magnetic separators, which precisely extract ferromagnetic metals like nickel or cobalt. The remaining fragments continue along the conveyor belt. A fine black powder, known as black mass, settles into specialized containers. This is where the real treasure lies: lithium, cobalt, and manganese. Machines use dust collectors to literally suck up the powder, ensuring even the tiniest particles are recovered. The remaining materials that can't be recycled, plastics and traces of electrolytes, are flushed out using specialized liquid streams. At this stage, hydraulic crushers grind the leftovers into a slurry that's easy to filter. Engineers monitor the crushers and the temperature inside the chambers. Specialists analyze the crushed material to ensure all metals have been separated and no unwanted contaminants remain. If a battery is still charged or has defects, it can literally explode during crushing. But don't worry, the system has it under control. Any explosion is immediately suppressed with gases, and the process keeps running smoothly. Once the batteries are shredded and that precious black powder is collected, the real magic, science in action, begins. Metals that seemed locked away forever are recovered using two main methods: hydrometallurgy and pyrometallurgy. It might sound a bit technical, but the processes themselves are fascinating. So, how does it work? The battery fragments are submerged in special acidic solutions. Imagine massive vats filled with bubbling yellow-green liquid, typically sulfuric or hydrochloric acid. When the fragments are immersed, a chemical reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve into this metallic soup. To extract specific metals, a clever trick called ion extraction is used. Special reagents, such as organic compounds, are added to the solution. These reagents act like magnets, binding to particular metals. The result? Each metal settles into a separate layer. Once the metals are isolated, they're precipitated as salts or hydroxides. These appear as tiny white or colored crystals. For example, lithium settles as lithium carbonate, resembling fine sugar. Cobalt forms a vibrant blue precipitate, while nickel becomes a pale green powder. If hydrometallurgy is the gentle approach, pyrometallurgy is more like shock therapy for metals. Everything here burns and melts. The black mass is loaded into a massive electric arc furnace, where temperatures soar to nearly 3,000 degrees Fahrenheit. The metals liquefy into molten layers, while plastic and other remnants simply burn away. The metals separate naturally, like oil and water, but at lava-like temperatures. Inside the furnace, several layers form. Heavy metals like cobalt and nickel sink to the bottom, while lithium remains in the slag, the lighter, upper layer. This slag is then broken apart and processed separately to extract lithium. Once cooled, the metals take the form of small ingots, shiny, smooth, and ready for reuse. Cooling after the pyrometallurgical process is typically a controlled procedure. If molten metals are left to cool on their own, it could take hours or even days. Plus, uneven cooling can lead to structural irregularities, which compromise the quality of the final product. That's why specialized chambers are used to regulate the cooling speed. For air cooling, ingots are placed on a conveyor under powerful fans. Imagine a giant hairdryer quickly cooling the metal surface. For water cooling, the ingots are submerged in tanks filled with water or special liquids for a faster process. As the red-hot ingots hit the water, they release dramatic clouds of steam, a visually stunning sight. There's also hybrid cooling, where the process starts with air cooling and finishes with water immersion. This method reduces internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse in batteries. It minimizes cracks or defects that can occur due to rapid temperature shifts. The extracted lithium is used to create new batteries, ones that will power electric cars or even your phone. Nickel becomes part of wind turbines generating clean energy, while cobalt plays a vital role in medical devices. This process literally closes the loop. Old batteries give life to new technologies. Discarded batteries can become an ecological disaster. First, they contain toxic substances that contaminate soil and water. Second, mining for new rare earth metals not only depletes natural resources, but also damages the environment. Recycling solves both problems. Here's the kicker. The more batteries we recycle, the less we rely on mining new materials. It's a direct path to sustainable development. Despite lithium's growing popularity, only 1% of this metal is currently recycled. The main reasons: high costs and the complexity of the process. But researchers are developing new technologies that could revolutionize this in the coming years. Interestingly, even now, electric vehicle manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to keep control over these valuable materials.